Thank you for the introduction. Can everyone hear me okay? Great. So thank you. It's a great honor to be here. I'm very excited to tell you about one of my favorite problems, interpolation for Brill Noether curves. And I will explain all the words in the title as we go. But before I get started, I just want to say a couple of things. First of all, almost everything original in this talk is joined with Eric Larson, who you see pictured here. He's also here, and I'm sure he'd love to talk to you about this. And second, I'm very receptive to questions. I know this room is not quite set up for it, but if you can shout a question out to me, I will repeat it for everyone. So it'll be a lot more fun for all of us if you ask questions. And I'm going to sort of prompt you to answer some of my questions, so be prepared for that. All right, let's get started. So the interpolation problem, in its most broad form, it says fix some collection of points in some space, and I'm always going to assume that those points are in general position. So there aren't any unexpected incidences between these points. If you were to bump them in random directions, that would disappear. Okay, and what are we going to ask? We're going to try to thread some curve through these points. And as you can see from this picture, I care about exact interpolation. I'm not asking something statistical about curve of best fit. I really want this curve to literally pass through all of these points. And the question we're going to ask about this is, if we fix the number of general points, then how complicated must the interpolating curve be? So I think it's probably intuitive to all of us that as you ask a curve to pass through more and more general points, it has to become more and more complicated. But to quantify this, we're going to flip the problem on its head and say that if we fix the type of curve, which bounds its complexity, then what's the maximum number of general points that that class of curves can interpolate? Is the question clear to everyone? Great. Okay, so as I said, audience participation. If I give you 2 points in the plane, what's the least complicated type of curve you can think of that interpolates them? Great, thank you. Nobody's shy. Lines. So yes, this was known to Euclid in 300 BC. Lines interpolate 2 general points. Great. Let's make it a little more complicated. What about 3 general points? Circles, you can do it with conics, but circles is even better. So yes, also known to Euclid, in case you want to look up the reference, it's proposition 5 in book 4 of the Elements. Right, so how could Euclid prove something like this? He's in fact giving the compass and straight edge construction of a circle interpolating 3 non-collinear points. And of course, we can't do better than 3, right? If we took 4 points, then they only lie on a circle if the polygon spanned by those points is a cyclic quadrilateral, which, as you know, is a special thing for quadrilaterals. So 3 is the maximum number of general points. Okay, so here are those 2 results that are there from classical antiquity. Lines interpolate 2 general points. Circles interpolate 3 general points. I want to point out one more, which sort of came up. Someone shouted it out. Conics. So this is also classical. It's in the collections of Pappus of Alexandria. So conics interpolate 5 general points. And again, Pappus was working in the time when this result was proved by some compass and straight edge construction. But I want to give you another proof of this result that with a slightly more modern flavor. And then as the talk goes on, I'll give you more and more proofs that become more and more sophisticated. So how do we prove this? Well, conics have equations, right? So a conic is specified by a non-zero affine equation of degree 2 in 2 variables, as I've written here, and the A, B, C, D, E, F, that's what tells me what conic I have, of course, and they can't all be 0. And this is perfectly set up for the interpolation problem because 5 points are on this conic if and only if, when I plug in the coefficients of those points to this equation, simultaneously all of those vanish. So this might look complicated, but let's remind ourselves it's not that complicated, right? Because these coefficients, these P's and Q's of the points, they're just scalars. They're just elements of the field. So the thing I actually want to find, the conic interpolating these points, that's just determined by the A, B, C, D, E, F. So you see that in terms of those, this is a linear equation. So let me rewrite it the way we'd ask our linear algebra students to do this. So I'm saying A, B, C, D, E, F is in the kernel of this matrix, right? So I have 6 variables, A, B, C, D, E, F, I'm trying to solve for, and this is a 5 by 6 matrix. And so what's the insight of this proof? A matrix with more columns than rows always has a non-zero kernel. And so I can find a non-zero A, B, C, D, E, F that satisfies this, and hence a conic interpolating these 5 points. And of course, I can't do more, because if I add another point, that adds another row to this matrix, so now I get a 6 by 6 matrix, and probably, if the points are general, provably, that has only 0 kernel. So this technique, I'm going to sort of summarize this as, say, linear algebraic proofs. And this was, you know, obviously, when linear algebra became an important thing, this moved the interpolation problem forward quite a bit, because it's very well attuned to solving the problem. So there's that result for conics. So let me see, can somebody in the audience tell me, using the linear algebraic proof, how many general points should a degree D plane curves interpolate?
D plus 2 choose 2 minus 1.
Thank you, thank you. D plus 2 choose 2 minus 1. Perfect. This first appeared in a paper of Kramer from 1750, Kramer of linear algebraic fame, right? He wanted to solve systems of linear equations in order to interpolate polynomials. Okay, so something I want to point out from this table, right? Circles, they're a special class of conic. They're less flexible than general conics, which is borne out by the fact that they interpolate fewer general points. So I could also ask for special classes of degree D curves among all degree D curves, and see, you know, that how the flexibility is constrained by looking at those special classes. So perhaps the most famous for the interpolation problem, if I say interpolation, this is probably what comes up into your head, is the Lagrange interpolation problem. So we fix our class of degree D curves to be graphs of degree D polynomials. And the reason why this is such a famous interpolation problem is because it has such a concrete interpretation. If I'm trying to interpolate a graph, then what I'm saying is that I'm trying to find a polynomial of degree D that sends some specified distinct inputs to some specified outputs. And what this Lagrange interpolation problem, which actually originally appeared in a paper of Waring, says is that you can do that with D plus 1 inputs. And that's the maximum number if they're general. All right, so that's a very natural and important class of degree D plane curves. Let me just make one more point here among degree D plane curves, right? If I'm fixing general points and I'm interpolating a degree D plane curve, I'm going to get a general degree D plane curve, so it's going to be smooth, so it's going to have genus D minus 1 choose 2. But if I want to fix what the genus of the normalization of this curve is, so I want to allow singular curves, I can do that. So degree D genus G curves interpolate 3D plus G minus 1 general points. And you may know that there's a beautiful story here. There's finitely many curves interpolating that many general points, and counts of these curves. There's a beautiful enumerative formulas. There's a lot of beautiful work stemming from this existence result. All right, so where do we go from here? So one thing we could do is we could say that was pretty fun. Let's stick with equations, but have more variables. So we could consider interpolating higher dimensional algebraic varieties specified by a single equation, but in more variables. So I showed you this extended linear algebra example of conics. So what if we just throw in one more variable? So we still look at degree 2 polynomials, but now in 3 variables. So this gives me quadric surfaces. So how many general points should a quadric surface interpolate? Everyone going like this is doing the right thing. 9, yes. Quadric surfaces interpolate 9 general points. This is going to come up again, so you all are going to remember, right? Okay, great. I'll ask you when it comes up again. But I think that wasn't very fun, right? That was just in the world of linear algebra. Kramer could have done this if he cared about it. So I want to go in a different direction. I want to put myself in the world where we're not going to be looking at subvarieties that are specified by the codimension many linear equations. I'm not going to be looking at complete intersections. So I'm going to stick with curves, but I'm going to allow more types of curves. I'm going to move myself out of the plane and look at general types of curves. So I just want to emphasize for you here that there's going to be 3 relevant discrete parameters that are going to come up over and over again in this talk. So there's the genus of the curve, which I'm going to denote with a G. There's the dimension of the projective space, which I'm going to denote with an R. And there's the degree of the curve, which I'm going to denote with T. So in this, it's going to be really relevant what G, R, and D are. All right. So the question that I want to focus on for the remainder of the talk is what's the maximum number of general points interpolated by curves of degree D and genus G in R-dimensional projective space? So when you see this question, there's a natural moduli space here. You could take the Hilbert scheme. I think from the point of view of the interpolation problem, it's a little more natural to take the space of maps. So I'm going to consider the moduli space of degree D maps from a curve of genus G to PR, and I'm going to denote that MGPRD. All right, so if you know something about this moduli space of maps or the Hilbert scheme, then you might be thinking this. So what does this symbol mean? Danger, danger, and what does it literally mean? Curves ahead. So I like both of those. There are many curves ahead, but also danger, right? So why danger? Well, this space can have multiple components. And all of those examples I showed you in the plane, they were irreducible moduli spaces. It's you know, I haven't chosen the correct discrete invariance, G, R, and D, or I haven't chosen fine enough discrete invariance if I'm getting some moduli space that has many components. Because why should I even expect that the number of general points is the same on these different components? It very well may not be, and we have examples where it's not. Also related to that, these components can have different dimensions. And if you saw all of the expectations you were doing from the linear algebraic proofs, you were counting the coefficients, you were counting the dimensions of these spaces. If they have different dimensions, I really would expect that to affect the interpolation problem. So this might look pretty bad, right? There's this zoo of components. I'm trying to answer this question. How do I pick out some natural class of components here? Might look quite difficult, but in fact, there is a most natural class of components in this space of maps, and it comes from the Brill Noether theorem. So the Brill Noether theorem is a theorem, as I've stated it here, combining work of many mathematicians in the 1980s over the complex numbers, sort of a crowning achievement of our understanding of linear series on curves. And so what it says, in terms of my invariants, G, R, and D, there's this simple inequality, the Brill Noether number, rho. So rho of GRD is G minus R plus 1 times G minus D plus R. If I plug my invariance into that and I get something that's greater than or equal to 0, then in fact it picks out for me a unique component in the moduli space of maps. And what picks out this component, first of all, is that the maps are non-degenerate. So that means that the curves span all of PR. They don't live inside a PR minus 1, which is very natural, right? A curve that maps to PR but just includes into a hyperplane, I don't really want to consider that as a map to PR. So I'm going to force my maps to be non-degenerate. But the crucial thing is that the moduli of the source curve is general. In other words, this map from the Brill Noether component, MGPRDBN, to MG is dominant. And conversely, if the Brill Noether number is negative, then no such component exists. So this picks out for me in this range, when this inequality is satisfied, this very natural class of components specified by saying that they are maps from general curves to projective space. So much more is known about this Brill Noether component, but as I sort of indicated on the last slide, it will be relevant to know dimensions. So, So the dimension of this component also comes out of the Brill Noether theorem. It has dimension R plus 1D minus R minus 3 times G minus 1. Okay, so you see there's a lot of space on this slide, right? And also I told you the original proofs were over the complex numbers. So Brill Noether theory is still a very active area of research today, and subsequently we know it in all characteristics, and we know much more about this Brill Noether component by the combined efforts of many more mathematicians, some of whom you see pictured here. So if you're a grad student, Brill Noether theory didn't end in the 1980s. There's a lot of really interesting stuff going on today. So because now I have this natural class, maybe I'll switch this one, because I have this natural sequence of components, the Brill Noether components, I want to focus on the curves parameterized by these components. So I'm going to call them Brill Noether curves, or BN curves for short. And it might look like I am abusing notation a little bit, right? The points in this are maps from curves to projective space. But I'm going to sort of think about that the same as the image, which is justified because a general such point is an embedding when R is at least 3. So I can really think about the map and the image as the same thing. All right, any questions about this up so far in the talk? I can't do anything with Zoom. So somebody could read the question from Zoom, all right, I'm going to go on, but if you want, interrupt me with the question from Zoom. Okay, so now that we have this natural class of components, we have an irreducible moduli space. It's the right time to ask our interpolation problem. So we're going to ask, what's the maximum number of general points interpolated by Brill Noether curves of degree D and genus G in PR? And of course, there's this moduli space here, the Brill Noether component of the space of maps, MGPRD Bn. And to try to understand what this maximum number of general points should be, I want to put these points into the problem. So I can do that. I can put them into this moduli space. So I can mark n points on the source curve. So MGN PRD. So it's the points of this correspond to a map from a genus G curve to PR of degree D, and n points on this, n distinct points on the source curve. And once I have these points, there's a natural evaluation map where I just say, where does F send each one of these points? I get a tuple of n points in PR, so I get this evaluation map. I'm calling it evaluation n to PR to the n. And now let's think about our question, right? Our question was saying, if I fix a general collection of points in PR, well, that's just a general point in the moduli space PR to the n. I want to thread a curve through it, so I want it to be in the image of this evaluation map. So our main question is exactly asking, what's the maximum n so that this evaluation map is dominant? Good? All right. So there's just that question again, what's the maximum n so that this evaluation map is dominant? Let's try to make a guess. So if you think about this question for about a minute, you will probably see that a necessary condition is that the dimension of the source is at least the dimension of the target, right? If it's smaller, there's no chance the map is going to be dominant. And I told you that the Brill Noether theorem told us these dimensions. So the dimension of the source, well, the dimension of the Brill Noether component is r plus 1d minus r minus 3g minus 1. And then I have n points, and each one of those can vary on my curve. So this whole thing has dimension n. Well, I add dimension n to this number. And then, of course, PR to the n has dimension r times n. And so doing a tiny bit of rearranging, you see that this gives me an upper bound on n from this necessary condition. So doing that dimension count, you would get the following folklore conjecture. A Brill Noether curve of degree D and genus G interpolates up to exactly the inequality coming from the dimensions, r plus 1d minus r minus 3g minus 1 over r minus 1 general points. Questions now about this conjecture or anything I've said so far getting us to this point? Yes? The conjecture is that this is the maximum number of general points. Exactly. Other questions? Thank you for asking. Other questions? Yes?
Is the ordering of the points relevant in the previous slide?
The order of the points is not relevant. Thank you. I should say, let me just make this clear. This space, the points, the moduli of the curve and the moduli of the points on the curve can vary here. It's not like I'm fixing them. Thank you. Other questions? For the degree of this evaluation map? No, in some special cases, there are things known, but no, that's a very interesting question. Oh, thank you. I said I was going to repeat it. The question is, when this is an equality, in other words, when I expect this evaluation map to have relative dimension 0, can you tell me that number? Can you tell me the degree of that map? All right, so any other questions? You're asking great questions. Keep them coming. Yes.
Is there any other geometry difference of this number except for the diameter?
The question was, is there any other geometric significance of this number? The real geometric significance comes from the dimension. You will see this magical number r plus 1d minus r minus 3g minus 1 appear again later in the talk, but it's really appearing for the same reason. Thank you. Good question. Other questions? Yes.
Here, the run, the actual quantity.
The question is it clear when you go to the boundary that it?
Yeah, so you have this boundary component that have bigger dimension. They might still not double.
Okay, tell me if I'm interpreting the question correctly. I think the question was, there are other components of the space of maps. Could those also dominate in this case? Is that the question?
Yeah,
Yes. In fact, we have examples where they interpolate more points than the Brill Noether component in the Brill Noether range. I can tell you this example afterwards if you want. Okay. So hopefully this conjecture is clear. I want to just do a couple of special cases. So the first one is when R is 2, right? We did at the beginning of this talk this extended example of interpolating plane curves. So when R is 2, if you plug that into this conjecture, you exactly get 3d plus g minus 1 points, and that is what we saw for the maximum number of general points for plane curves of degree d and genus g. So that's good. I want to do one more special case, which is when R is 3, which is pretty nice because all dependence on the genus drops out from this conjecture. So when R is 3, you see that it just conjecturally predicts that a space curve of degree d should interpolate 2d general points. All right, so I'd like to do an example. Does someone have a favorite? I'm nervous to ask this. Does someone have a favorite class of space curves? Okay, twisted cubics will come up at the end, but I'm going to do canonical curves. Canonical curves. So G, R, and D are 4, 3, 6. So the conjecture predicts twice the degree many points. So that's 12 general points. So if you know something about canonical curves, if you're friends with them, then you probably know that every canonical curve of genus 4 lives on a quadric surface. But even if you don't know that, it's very easy to prove. It's an easy consequence of the Riemann-Roth theorem. It's sort of grayed out here. You can see it. So I said quadric surfaces were going to come up again. Who remembers the relevant thing about quadric surfaces? They interpolate 9 general points. So is that good? We're hoping that these curves interpolate 12 general points, but any 12 points on one of these canonical curves lives on a quadric, which means that it is necessarily a special configuration of 12 points. So we have a counterexample. Maybe the first class of curves that you all shouted out to me that I should consider already gave a counterexample to this very natural conjecture. And moreover, if you search around, you will see that this idea gives you some other counterexamples too. So here's the invariance. So in three-dimensional space, in P3, there's the canonical curve example, genus 4 degree 6. So for a very similar reason, genus 2 degree 5 is also a counterexample. So the conjecture predicts twice the degree, that's 10 general points. But again, every such curve lives on a quadric surface. And so the maximum number of general points it could interpolate is the number interpolated by the quadric, which is 9. So we have these two counterexamples in three-dimensional space, and I think about them as obstructed by this quadric surface, right? They're this surface that every curve lies on. The surface doesn't pass through the right number of general points, or the number of general points required by the curve. And actually, it's even a little bit worse. So each one of these counterexamples has a friend in 5-dimensional space. So, so this genus 2 degree 5 curve, also genus 2 degree 7 in 5-dimensional space, and canonical curves in P3, also canonical curves in P5 are a counterexample. And we understand why they're counterexamples also. They're also obstructed by surfaces. So let me move over here. So let me explain to you first this one of the genus 2 example. So genus 2 curves are hyperelliptic, which means I can take pairs of points that are conjugate under the hyperelliptic involution, and I can join them by lines. So if I do that, I'll get some scroll swept out by these lines that has to contain my curve. And that hyperelliptic scroll, that scroll coming from the hyperelliptic involution on the curve, only passes through 9 general points, even though the conjecture would say that the curve passes through 10 general points. And let me note that in this case of genus 2 degree 5, the quadric is this hyperelliptic scroll. And then canonical curves of genus 6. So if you're friends with canonical curves, you might know that a general such one is a quadric section of a del Pezzo surface of degree 5. And the del Pezzo surface of degree 5 only passes through 11 general points, despite the fact that the conjecture says the curve should pass through 12 general points. So the exact numerics here don't matter so much, but the idea is there are these surfaces that get in the way. All right, so if you look at these counterexamples and you look at our very natural conjecture, and you have a true dose of optimism, you might make the following conjecture, which I'll call the optimist's conjecture, which says that the dimension count conjecture holds if and only if you aren't one of these 4 counterexamples. So with a true dose of optimism, you can try to make this conjecture. And it might look, you know, a little bit harebrained, a little bit overly optimistic, given how natural these counterexamples were. Nevertheless, there has been a lot of work on this conjecture starting from the 80s. So I won't go through all of these in detail, but the case of genus 0 curves, the case of canonical curves, the case of curves that are embedded by a general line bundle, so non-special curves, and then space curves and curves in 4-dimensional space. We know the optimist's conjecture in all of these cases. So we know it, but this leaves out many, many, many of the most interesting tuples, G, R, and D of Brill Noether curves. And furthermore, all of these results, at least the ones I've highlighted in red, crucially assume that the characteristic of the ground field is 0. And the only reason genus 0 is not there is because you can reduce to characteristic 0 from positive characteristic. So the main theorem I'd like to tell you about today is that the optimist conjecture is true in full generality and in arbitrary characteristic. So explicitly, that is, for any tuple of invariance, G, R, and D, such that the Brill Noether number is greater than or equal to 0, there exists a Brill Noether curve of degree D and genus G in R-dimensional space, interpolating the expected number of general points, so R plus 1D minus R minus 3G minus 1 over R minus 1, if and only if it is not exactly one of these counterexamples. So this is an if and only if theorem, but really we understand why these are counterexamples. The number of general points is respectively 9, 9, 9, and 11, just the number that the surface can interpolate. So the real content is the converse. It's that if you have any other G, R, and D, it does interpolate this expected number of general points. All right, questions about this theorem? All right, so how do you prove a theorem like this? Well, it's really a triply infinite collection of theorems for every tuple G, R, and D that satisfies the Brill Noether inequality. So when you see that you have a triply infinite collection of theorems, you might imagine maybe we should do induction. Maybe we should try to take our invariants G, R, and D and reduce the interpolation problem for those invariants to interpolation for smaller invariants. And I want to say 2 things about this. First of all, the presence of these counterexamples means that whatever inductive argument you have necessarily has to be relatively complicated, because you can't ever have an inductive arrow that points down to a counterexample, right? That would be a very bad inductive strategy. So your induction can't be relatively simple. It has to be complicated enough to exactly never point to one of these counterexamples. And second, if you're thinking about doing this induction with G, R, and D, then G, R, and D mean something, right? They're the genus, degree, and dimension of the projective space. So you might imagine the way to reduce that tuple to smaller tuples is to break your curve into curves that have smaller tuples. And so that is exactly the strategy that we employ. And I'd like to illustrate this in the simplest possible case. Definitely does not show all of the complexity of the argument, but I would like to reprove for you Pappus's theorem that conics interpolate 5 general points using this strategy of breaking the curve. So what I'm going to do is I'm going to start with a degenerate conic, a broken conic, a union of 2 lines, and 5 points on that union of 2 lines. So necessarily, if I have to put 5 points onto 2 lines, I have to put 3 points onto one of the lines. So these are very much not a general collection of points, right? It contains 3 collinear points. But what I can do is I can deform the points to be in general position. And then my goal will be to deform the conic along as I deform those points to be general. Clear to everyone? Great. So there's that problem again. I just like to deform the degenerate conic along as I deform the points to be general. And the reason why this is easier than the general case of this is because we can use the equations. We have equations in the plane. So a first order deformation of the conic specified by xy equals 0, well, I just have to add a really small parameter times some other quadratic polynomial in x and y. And this is a first order deformation, so I'm going to assume I'm adding an epsilon multiple where epsilon squared is 0. Okay, so I want this deformed conic to pass through my deformed points. So let's focus on one of those. Let's suppose we started with a point that began life on the x-axis. So let's say at a comma 0, and I deformed it to a plus alpha epsilon comma beta epsilon. So if I want my deformed conic to pass through this deformed point, then what should I do? Well, I just plug it in for x and y. So that becomes a plus alpha epsilon beta epsilon plus epsilon times q of a plus alpha epsilon beta epsilon equals 0. And this is quite nice now, because remember I assumed that epsilon squared was 0. And so a lot of things cancel, in particular all dependence on epsilon in this quadratic equation goes away. And so this is exactly saying that I want to find a q where q evaluated at the original point on the x-axis takes some particular value. The value itself doesn't matter very much. Does this sound familiar to anyone? I want to find a quadratic polynomial on the x-axis that takes some specified value at some specified point. Yes? Yeah, it's Lagrange interpolation, right? Lagrange interpolation tells us that we can find a quadratic polynomial on the x-axis taking specified value at 3 points. And look, we had 3 original points on the x-axis where we'd like our deformation to pass through the deformed points. So that's something about finding a q that takes some specified value at the original points. All right. Well, what's stopping us? We took these 3 points on the x-axis. Let's now move and look at the y-axis. So again, Lagrange interpolation tells us that we can find a quadratic polynomial in y that takes a specified value at, well, 3 points on the y-axis. It looks like I have an extra degree of freedom. Why can't I make conics pass through, interpolate 6 general points using this? Yeah, they have to, I have an agreement condition at the origin, right? I don't want to mess up whatever happened on the x-axis. So say I have to make it take value 0 at the origin, not to mess up what happens on the x-axis. And then I can use this broken problem and piece it together and find such a interpolating conic. All right, so that is That is the equation proof of Pappus's result, but using deformation theory. Any questions about that? All right. So the strategy in general is quite similar. So I fix the correct number of general points that are in the image of the evaluation map. That means they live on some curve, of some Brill Noether curve of degree D and genus G in PR. But those points may not be general, just like the 5 points on the broken conic. They may not be general points. But then I'm going to ask, can I deform the map that gives rise to those points as I deform the points to be general? So said another way, using our moduli spaces, there's a natural map from deformations of the map FC to PR together with the points P1 through Pn on the source curve to deformations of the images of those points, which is just, I see where they go. So this question, this strategy, I'm trying to take some general deformations here, and I'm trying to lift them to deformations of the map. So I'm trying to show that, that I have a lifting of deformations here. And if you know something about the infinitesimal lifting criterion, then what I'm trying to show is that this map, the evaluation map, is generically smooth at some point, or it's smooth at some point and hence generically smooth. And generic smoothness is equivalent to dominance in characteristic 0, but it is not equivalent in positive characteristic. There could be some inseparable behavior here. And so I really am trying to show something stronger in positive characteristic. All right. So deformations. We have to understand deformations. So let's try to think about how do we parameterize deformations of this map, or I told you a general such point is an embedding, so let's think about embedded curves in projective space. Well, the first order deformations correspond to sections of the normal bundle of this curve, and in fact, the normal bundle is what controls the deformation here. So I've shown you a little picture, right? If I wanted to form this embedded curve, well, locally around each point, I have to tell you where that point moves in the projective space, or I have to give you some tiny little tangent vector at each point. But that's not quite what I want to show you, right? Because I'm not deforming the map. I'm not like saying that C has to stay fixed and I'm telling you where each point in C goes. I really want to deform the image. I'm allowing the curve to change in moduli. And so, here's another way of giving you tangent vectors everywhere that gives you the same deformation, right? I could have a little nearby point goes to each one of these points. And I want to consider those to be the same, right? I'm not telling you exactly where each point goes, just what the image looks like. So, okay, so what does that mean? Well, the difference between any two of these tangent vectors along the curve, you can see it's a tangent field to the curve. Hopefully you can see that drawn in blue. So that really justifies why I'm looking at the normal bundle, right? Telling you where each point goes locally. That's like a section of the restriction of the tangent bundle of PR to the curve, but I have to quotient by things that are the same modulo tangent vector fields along the curve. So I really do get the normal bundle. Okay, so the normal bundle controls the deformation theory. So you might imagine that this deformation problem, this infinitesimal lifting criterion I need to check, is phrased in terms of the normal bundle. So here's that problem, that lifting problem we're trying to understand. So the machinery of deformation theory tells you obstructions to smoothness of this evaluation map, or to this lifting problem. They live in the first cohomology of the normal bundle twisted down by these points P1 through Pn. So what that means is, if you want to show smoothness, or you want to show these deformations lift, then the easiest way to do that is to show that this cohomology group is 0. Because then there will be no obstructions to lifting these deformations, and we'll be good to go. The map will be generically smooth, so it will be dominant. Okay, so the normal bundle, or maybe let me see if I have any questions here so far with this turning it into a problem in deformation theory. Great. So the normal bundle, it's a vector bundle on this curve, right? And I want to show that its first higher cohomology vanishes. But we're on a curve, so there's only 2 cohomology, possibly non-zero cohomology groups, right? H0 and H1. And the difference between these groups is entirely numeric. The difference between the dimensions of these groups is just the Euler characteristic, which is given to us by Riemann-Roch. So I would be totally dead in the water if this, if the Euler characteristic of the normal bundle twisted down by these endpoints was negative. Because then that would say that H0 minus H1 is negative. In other words, H1 must be non-zero. So let me write down that Euler characteristic calculation for you. So the Euler characteristic of the normal bundle twisted down by these endpoints, that's the same thing as the Euler characteristic of the normal bundle minus the rank of the normal bundle, that's n minus 1 times little n. And now here's where I said that this magical number was going to come up again for very good reasons. The Euler characteristic of the normal bundle is the dimension of the Brill Noether component for good deformation theory reasons. So this is r plus 1d minus r minus 3g minus 1. So you see that the Euler characteristic of the normal bundle twisted down by these endpoints is greater than or equal to 0 precisely when n is at most this maximum value up here, right? This maximum that I got here from my dimension conjecture is exactly saying, it's the same thing as saying the Euler characteristic of the normal bundle twisted down by these points is greater than or equal to 0. So it's exactly the condition when we could hope to prove that this bundle has no H1. All right, so hopefully the following definition will seem well motivated to you given that context. So we say that a vector bundle on a curve satisfies interpolation if for all integers n greater than or equal to 0 and n general points on my curve, if I take my bundle and I twist it down by those points, I have at most one non-zero cohomology. So I have sort of expected cohomology when I twist down by points. So that is either H0 is 0 or H1 is 0. And when n is 0, there's only one effective divisor of degree n, namely the empty divisor. So I furthermore require that it's H1, that's 0. So this condition, it's exactly saying that when you could possibly have only one non-zero cohomology, or I guess you could always possibly, let me say it another way, when the Euler characteristic is greater than or equal to 0, you have no H1, and when the Euler characteristic is less than or equal to 0, you have no H2. So by what I said on the previous slide, hopefully you see that if I can find a single degree D, genus G, Brill Noether curve, for which the normal bundle satisfies interpolation, then when I twist down by general points, I will have no H1, so I will have no obstructions to smoothness, so I can lift my deformations, and I get dominance, I get everything I want. The optimist's conjecture holds for that. So our new goal is to study this interpolation property for the normal bundle. So how should you think about interpolation? Well, I'd like to give you a feeling for this property of the normal bundle, property of a vector bundle in general, by giving it to you in the easiest possible example. So let's suppose our curve is P1. So then every vector bundle on P1 splits as a direct sum of line bundles. So I'm going to write it as O of A1 through O of AR minus 1. So this A1 through AR minus 1, they're the invariants that sum to the degree of the bundle. And it satisfies interpolation if and only if. Well, let's take each one of these properties in turn. So first of all, there's this positivity property that says H1 has to be 0. So if you wind that out to what it means for this bundle on P1, then you see that it says that all of these AIs have to be at least minus 1. So interpolation, it encompasses this positivity requirement on my bundle. And second, there's this part that says it has to have expected cohomology when you twist down by general points. Well, let me give you an example. Let's suppose that my bundle was O of 5 plus O of 7 on P1. Does that satisfy interpolation? Well, you could twist down by 7 general points. Then you'll get O of minus 2 plus O. And that has both H0 and H1. So that bundle does not satisfy interpolation. It does not satisfy this condition. And what let me do that was that 5 and 7 were sufficiently far apart that I could twist down by one of them and pick up an H0 and an H1. So if you work that out in general, it's not so hard to show that in fact the differences between each one of these, this condition is equivalent to saying the differences between these AIs are at most 1 for all I and j. And this condition, the second condition, is saying that the bundle is balanced. And if you know something about vector bundles on curve, then you know balance is the closest to stable that you can hope for on a genus 0 curve for your vector bundle. It's related, it's, you know, yeah, it's the closest you can, it's the best, most stable you can hope for. And in general, in fact, interpolation is you should think about it as a stability, a semi-stability like property. It is neither weaker nor stronger, even taking into account that it contains this positivity condition. But sometimes it's stronger. So if the rank of your bundle divides the degree of your bundle, then interpolation implies semi-stability. So anytime I state a theorem for you proving interpolation for some bundle, and that bundle has integral slope, then I have also proved semi-stability. All right. Questions about this property of vector bundles on curves? Okay. So back to our upshot, right? Using the package of deformation theory, we have to show that there exists a Brill Noether curve of degree D in genus G whose normal bundle satisfies interpolation. So the first main theorem is the consequence of the following more precise main theorem, which says the normal bundle of a general Brill Noether curve of degree D and genus G in PR satisfies interpolation if and only if neither of the following occurs. First, in all characteristics, your tuple GR D could be one of the following 5 counterexamples. Or, interestingly, the characteristic could be 2, the genus could be 0, and your degree could fail to be congruent to 1 modulo R minus 1. So I want to say something about each of these 2 classes of counterexamples. So the ones that hold in all characteristics, you notice I now have 5. I've snuck in for you another counterexample, right? There's this sort of family of genus 2 curves in R-dimensional space of degree R plus 2. I've snuck in for you the one in P4 in between the previous one in P3 and the one in P5. So what's going on there? Well, in this case, the conjecture predicts, the optimist conjecture, predicts that such curves should interpolate 9 general points. And in fact, if you take the normal bundle and you twist it down by 9 general points, it has no H1. So you have no obstructions to smoothness, to generic smoothness of the evaluation map, and you can prove the optimist conjecture. But if you twist down by 1 more point, if you twist down by 10 general points, then you have both non-zero H1 and non-zero H0. And so it does not satisfy interpolation. So you might imagine that this fact that the optimist conjecture and interpolation for the normal bundle are different is some illustration of the fact that in this case, the normal bundle does not have integral slope. And when I twist down by points, I change the Euler characteristic, or I change the Euler characteristic over the rank by integers. So somehow I want to twist down by something smaller than points, right? That will affect it not by integers. And so, in fact, the sort of geometric incarnation of this cohomological fact is that, in fact, interpolation for the normal bundle implies something much stronger in geometry. It implies expected incidences to linear spaces of any dimensions. So, I'm looking for a curve that meets this 2-plane, passes through these points, and meets this line, something like that. And the codimension that you expect depends on the dimensions of these linear spaces. And so in that way, you can fix this non-integrality property that I was saying. So for this class of curves, for curves of genus 2 and degree 6 in 4-dimensional space, you expect them to pass through 9 general points and meet a general line, and they can't do that because the surface, the scroll that contains them, does not do that. So that's the geometric reason for this 5th counterexample. So I now want to say something about the characteristic 2 counterexamples, because that's perhaps rather interesting that comes up here. So in all characteristics, you have an Euler sequence for the normal bundle. Perhaps you're more familiar with the Euler sequence for the restriction of the tangent bundle, but you can further quotient to get something for the normal bundle. So if my curve in r-dimensional space is specified by r plus 1 sections of the line bundle O of 1, then I have a natural map from the trivial bundle of rank r plus 1 to the first bundle of principal parts of OC of 1, which takes the value and the derivative of each one of those sections at every point. And the twist of the conormal bundle is the kernel of this map, what the Euler sequence says. So that's in all characteristics. That wasn't a characteristic 2 phenomenon. But in characteristic 2, this map I just described for you is a pullback under the Frobenius morphism. Maybe that shouldn't be so surprising, right? Because what does it mean to take the value and the derivative at some point? It means to restrict this line bundle to that first infinitesimal thickening of that point. And those thickenings are the fibers of the Frobenius morphism in characteristic 2. So if this map I described for you is pulled back under Frobenius, then this conormal bundle twisted by 1 is pulled back under Frobenius. So if the genus is 0, this bundle splits as a direct sum of line bundles, right? O of A1 through O of AR minus 1. But it's pulled back under Frobenius. So that says each one of these AIs has to be even, right? It's pulled back under a degree 2 morphism. But it's very hard for a bunch of even numbers to differ by 1, right? Interpolation is differing by 1. So the only way they can differ by 1 is if in fact they're all equal, which says that the degree, namely the sum of them, you have some congruence condition, and that congruence condition, if you take out this twist, it translates back exactly to say that D must be congruent to 1 modulo R minus. So, but I told you that the theorem, the optimist's conjecture, holds in genus 0. So what's going on? The evaluation map is dominant, but it's not generically smooth. You have some inseparability coming from this Frobenius. All right. I would just like to take a few more minutes and just tell you the very high-level overview of the proof. So the very high-level overview is that the semi-continuity theorem says that interpolation is an open condition in families, right? It's something about cohomology vanishing. So it's an open condition, which says that we are free to degenerate. We're free to break our curve. So I'm going to move to the boundary of the moduli space. So I'm going to consider this moduli space of stable maps, which in particular allows the source to be a nodal curve. And when I have an embedding of a nodal curve, the normal bundle still makes sense. The dual of I mod I squared is a vector bundle, which is the normal bundle. So I'm going to be particularly interested in reducible nodal curves like this. So how do we understand this normal bundle of this reducible nodal curve? Well, it's a vector bundle. I can take it and I can restrict it to each one of the components. And now, right, the normal bundle parameterizes deformations. And so if I think about those deformations along any one of these components, well, of course, what could I do? I could just deform that component itself. So this normal bundle of the union along any component, it has a subsheet, which is the normal bundle of that component. So that's like saying I have this reducible curve. Well, if I move x around, if I deform x, it induces a deformation of x union y. But if you think about that, if you think about moving this component, you'll see there's no way to ever smooth that node by just deformations along that component, right? They're going to be equisingular. And so, but I've shown you these pictures of hyperbolas smoothing unions of two lines, right? So it is, I mean, of course it's possible. This is the boundary. I can move to the interior. I can smooth these nodes. So let's look at this deformation from the perspective of x. So along x, you see that if I'm drawing this section of the normal bundle, as I get closer to this node, it acquires a singularity, right? These points go off to infinity. So this normal bundle of x is a subsheet, but in fact, the normal bundle of x union y restricted to x is more positive. I allow holes in the direction of this other component. So this is formalized in this result of Hartshorne and Hershowitz. So if I take the normal bundle of the union and I restrict it to one component, then it's what's called a positive elementary modification of the normal bundle of that component at the points where they meet, where you're allowing pulls towards the other components. So the idea is to break your curve in such a way, choose a y, where you can reduce interpolation for the normal bundle of the union to interpolation for the restriction to one component, possibly with some other modification that allows for the gluing condition to the component y. So we'd like to use this to break off pieces to get smaller and smaller curves, and each time we have to take some modification of the normal bundle. So the difficulty with this idea is that iteratively degenerating produces more and more and more modifications. And it's bad for induction if you have something that increases as you're doing your induction, right? That's not very good. So that's one difficulty. Before I solve that difficulty, I'd like to tell you about the second strategy. The second strategy is to put into this induction is to reduce the dimension of the projective space. And we'll do that by projecting from points. So when we project from points, I'm going to project from a point on the curve. We have this normal bundle exact sequence. So I have tangent directions, normal directions that sort of live in this cone that you can see that point towards P. I'm going to call that subbundle of the normal bundle NC to P, the normal directions pointing towards P. And in fact, if P is a sufficiently general point, that bundle is isomorphic to O of 1 twisted by 2P. So those normal directions, they get contracted by this projection map. And so the quotient is roughly the normal bundle of the projection, but I have to twist by P for the fact that I'm projecting from a point on the curve. Okay, so we have this exact sequence. I'd like to illustrate this for you in the case where it works the best. So I did promise to prove interpolation for you for one more class of curves. Does anyone remember?
Twisted cubics.
Twisted cubics, okay. Let's do twisted cubics. So for twisted cubics, rational normal curves in P3. They're embedded by a line bundle of degree 3. So this OC of 1 is degree 3. I've twisted by 2 points. I get an O of 5. The image is a conic, so its normal bundle is an O of 4, and I've twisted by a point, so I get another O of 5. And so you see from this exact sequence that if I twist down by 6 points, the conjecture predicts twice the degree, right? 6 points. You see that my bundle is smooshed between bundles that are an O of -1 and an O of -1, which have no H1, and so it has no H1, and I have smoothness, and it's great. But this strategy also has a difficulty, which is that this projection exact sequence, it was very nice in this case. It was balanced, right? The slopes of the sub and the quotient were the same as the slope of the central term. But in general, the slope of the sub, the degree of the sub, is going to be it's going to be smaller. And that is just the case in which this tells me nothing when I twist down by the right number of general points. So here are those two difficulties. And the last amazing thing I want to tell you is that each of these difficulties is a potential solution to the other difficulty. So why is that in an impressionistic way? Remember that if I take this normal bundle and it's going to have some positive modifications, I'm allowing some poles. If I can line up those poles to point towards P, then they contribute, they twist up the subbundle. And so they bump this sequence to be closer to being balanced. And also, I've taken those modifications and they were in the directions that got contracted by the map. So I've also eaten those modifications and they don't show up in the quotient. So I have both made my sequence more balanced and I have consumed these accruing modifications. So why did this not solve the problem before? Or why is this still a very complicated argument? It's because I need to be able to line these modifications up to point towards P. And if you were to do some random degeneration and keep track of the modifications of the normal bundle, you would not have the flexibility to specialize enough of those modifications to exactly work in this machine. So a miracle that makes this argument work is that there exists some very nice deformations where if you did a dimension count, you would not expect to be able to line up the points to point towards P, and yet there's some unlikely intersection that allows this to work. And that's what makes the whole argument go. So with that, I would like to say thank you and ask for questions.